As the bonds in the fan, this carbon atom over here, they would be pointing in certain directions. So if the H atoms are pointing in the same direction downwards, that's cis. And if they're pointing in opposite directions, they're still attached to the same carbon atom. It's not that they are structurally different, except that the orientation of the bonds in space is different. So that's going to be your trans isomer. So same groups pointing in opposite direction. And I told you that you can't really do that in cyclic structures, because for cyclic structures, you would have to break the structure. In cis and trans isomers, you don't break the bonds. The orientation of the bonds is just different. So we were at this point that if a molecule has multiple chiral carbon atoms, what happens then? Or multiple double bonds. So what happens in that case? So if a molecule has multiple double bonds, so I'm going to do a molecule which has multiple double bonds. So you've got a double bond here and you've got a double bond here as well. And the first one, the very first one is, so the very first one is bonded to two different groups. There's an H over here, and this one as well. And there's an H over here, and there's an F over here. Now, this is an unsymmetric molecule. So this one is unsymmetric. What unsymmetric means is that the molecule, the left and the right side are different. I mean, there is no symmetry. You've got a fluorine on this side, you've got a chlorine on that side. So it's an unsymmetric molecule. So just by looking at the molecule, you can figure out that the molecule has no symmetry whatsoever. So we're going to talk about cis and trans isomers in unsymmetric molecules first. Now, the condition for a geometric isomer was that there must be a double bond. So we've got a double bond. And the second condition was that the groups must be different. Like each carbon atom must be bonded to two different groups. So it's bonded to an H. This one is bonded to a Cl. This one is bonded to an H. And on one side, there's this entire thing. Similarly, so this one in three dimensionals would exist in two forms. One would be cis and the other one is going to be trans. This other one is also going to show geometric isomerism. Because if you look carefully, the carbon atom is bonded to two different groups, and this carbon atom is also bonded to two different groups. It's got an H and it's got this entire carbon chain on one side. So the conditions are met. Both of them are going to form cis and trans isomers. So I'm going to draw the three-dimensional representation of this molecule, which is that around the double bond, the carbon atom is going to be fan-shaped. So around this double bond, the shape of the molecule is that the carbon atom is going to look like this. Okay, so whenever, according to shapes of molecules, whenever you've got a double bond in carbon atom, okay, that is fan-shaped. So whenever there's a double bond, the carbon atoms, the angles are 120 degrees, and you've got a pi bond on top and below. So there's a pi bond on top of it. There's a double bond here. So it is fan-shaped. That's the shape of the molecule. That's the shape of the first one. This carbon atom is bonded to H and Cl. So I'm going to add the H and I'm going to add the Cl as well. So this carbon atom over here, if you look carefully, that's bonded to an H and it's bonded to a Cl. This one over here is bonded to an H. So I'm going to put an H over there. And on the other side, it's bonded to another carbon atom, and that carbon atom is also making a double bond, right? It's the next one, this one over here. This carbon atom over here is bonded to an H and it's bonded to this thing. So it's bonded to an H, it's bonded to this double bond. Again, the three-dimensional shape of the molecule. Around the double bond, the molecule is fan-shaped. So the angles are 120 degrees. So I'm going to draw this thing now. So this carbon atom has an H. So I'm going to put in the H over here. And the other carbon atom at the end has an H and an F. So I'm going to put in an H and an F. So this here is the three-dimensional view of the molecule. That is the structural formula. Remember, the structural formula just shows the connections, like which atom is bonded to which atom. It doesn't show you the actual shape of the molecule. This one is the actual shape of the molecule. So remember, double bonds, fan-shaped. Now, the first one over here, this one is our cis version. Why is it a cis version? Because both H atoms are pointing in the same direction. So the double bond, I mean, the shape of the molecule, that's a cis shape. This one over here, this double bond is also a cis molecule, a cis version, because both H atoms are pointing in the same direction. So both of them are cis. The first one is cis and the second one is cis. Remember, both double bonds can exist in both forms, cis and trans. This one can also exist in cis and trans. So the version I've drawn over here is the one where both of them, they exist in cis versions. I mean, both of them, they exist in cis form. Is this clear? This one? Everyone, is this clear?
Yes.
Yes. Okay. Now, I'm going to draw the other ones. Let's say the first one is cis and this one is trans. So I'm just going to copy this molecule, kind of make it smaller. So I'm just going to copy this. I'm going to draw the other version, which is going to be exactly the same, except that the orientation of the bonds is going to be different, which means that over here, this one is not going to be cis. I want to make it trans. Now for trans, the H atoms must point in opposite directions. So what I can do is, instead of this H atom connected below, I mean, the direction of the F is going to be downwards. And the H, remember, it's still connected to the same carbon atom. So structurally, it is the same molecule, except that the orientation of the bonds is now different. So now you have one of them is, I mean, the first one is cis. I mean, both our H atoms are pointing in the same direction. The other one, that's your trans molecule. So this one is our trans version. So the two molecules kind of look the same, except for one difference. Over there, the F was pointing upwards and the Cl was pointing downwards. Over here, the Cl over here is pointing downwards and the F is also pointing downwards. So the shape is, the only difference is the shape. The connections are exactly the same. I mean, these two are still bonded to the same carbon atom, except the direction of the bond is different. So is cis and trans clear? Is this clear to everyone? Yes or no? Is this clear? Yes. And there are going to be two more. There are going to be two more versions of this molecule, three-dimensional shapes of this molecule. So I'm going to draw the other two. So I have a cis version, I have a cis trans version. I can have the first one as trans and the second one as cis. So we can just alter this. This one can be trans, and this one over here can be cis. Now, if I have to do that, I would have to switch these sides. I'm going to make the H point downwards. Okay, so there's going to be a completely different molecule where the H and Cl are still connected to the same carbon atom, but in a different way. So that's our trans version now, because the H is now pointing in opposite directions. And similarly, so that's our trans version. The other one, I have to make it a cis version. So the H atoms must point in the same direction. So let's pick that up, and that goes down. So remember, this is a completely different molecule. I'm not changing the same molecule. It's a completely different molecule where the H atom was always downwards. So you've got a trans and cis, and the last one would be trans and trans. Both of them would be trans. So just change this side, make this side. I'm just going to change the position of these two. I'm going to make this trans. So the H must be pointing downwards and the Cl must be pointing upwards. Like, I mean, the H atoms must be on opposite sides. So all four molecules are they kind of look the same, but they have very tiny differences. The tiny differences are Cl and F are, I mean, F is pointing upwards, Cl is pointing downwards. Cl is pointing downwards, F is also pointing downwards. F is pointing upwards, Cl is also pointing upwards. Cl is pointing upwards, and our F is pointing downwards. So there's just tiny differences between the molecules. The shape of the molecule is different, that's it. So here's an example of a molecule having two double bonds. So how many total isomers you got? You got 4 of them. You got 4 of them because if you get 2 double bonds, you can you can make up all the combinations. Like the first one would be cis, and the second one would also be cis. The first one would be cis, and the second one would be trans, and so on. The first one would be trans, and the second one would be cis, and the last one would be that both of them would be. Just 1 second. So the last one would be that both of them would be trans. So it's like maths, it's combinations. So you've made up all the combination, and the simple rule is you can use 2 to the power n, where n is the number of double bonds that are making cis trans. So quickly tell me, if you've got 3 double bonds in a molecule and all of them make cis trans, so how many total combinations do you have? Like how many different cis and trans isomers would you end up with if there were 3 double bonds and each one was making cis and trans?
8.
Okay, that's going to be 8. You can try up all the combinations. Like I'm not going to do all of them, just and you might be asked to draw a particular one. For example, so now I'm not going to waste my time drawing all of them. So here's my molecule. And the molecule has 3 double bonds. And each one of them, so this one has got a Cl, this one has H and H. This one has an H, and over here there's an H and F. So each one of them fulfills the criteria for a cis and trans. Like you got a double bond, that's one requirement. Both groups must be different. Over here, both groups must be different. You've got an H and you've got this entire carbon chain over here, so that both sides are different. So it's going to exist in 2 forms. This one also, it's going to form cis and trans. You got a double bond. Each carbon atom must be bonded to 2 different groups. You got an H and you got this entire carbon chain. You got an H over here, you got this entire carbon chain. This is 1 H missing. Let me add that. And this last double bond is going to be kind of the same. It's going to form cis and trans. So you can try up all the combinations. I mean, the first one could exist in cis and trans, both forms. The second one could also exist in cis and trans forms. And the third one could also exist in cis and trans forms. The shortcut is 2 to the power n. You got 3 double bonds, all of them are making cis and trans. So it's 2 to the power 3, which would give you 8 total different. There would be 8 different shapes of this molecule, 8 different orientations, 8 different isomers, which have the same bonding, except that the direction of the bonds are different. So they're going to be a total of 8 isomers. So, and you can keep on trying the combination. The first one could be cis, this one could be trans, this one could be trans. The first one could be trans, this could be cis, this could be cis. So there would be 8 different combinations. Is this clear?
Yes.
Okay, everyone, is this clear? Mareem, is this clear?
Yes, sir.
So you might be asked to draw a particular combination. For example, they might ask you to draw this one. That the first one is in the trans shape, the second one is in the cis shape, and the last one is also in the trans version. So remember, draw the double bond. The first one, around the double bond, the shape of the molecule is fan shaped. Okay, just like a fan. Then that carbon atom is connected to the next double bond. Around that double bond, the carbon atom is fan shaped as well. And then this carbon atom is connected to the next double bond. So around that double bond, the carbon atom, balki we can talk about that later. Okay, let's not jump onto that one. Because the middle one was, let's start with the middle one. The middle one was cis. That means both H atoms over here, they must be pointing in the same direction. So the middle double bond, I'm going to put the H atoms pointing in the same direction. Okay, because that's a cis version. So the H atoms must be pointing in the same direction. So double bond, it's got H atoms. I mean, the H could be pointing downwards. This one could be pointing upwards. That would have been a trans version. But he wanted a cis version. The first one was trans. For trans, the double bond has 2 carbon atoms. Each carbon has 2 hydrogen atoms. So for trans, the H atoms must be pointing in opposite direction. And over here, you've got an F. So the first one, yes.
You know how 2 cube is 8? What does it mean, like 8 what?
8 different molecules having 8 different shapes. I mean, for example, over here, I just showed you that. This would be 2 to the power 2. I mean, if you want to find out, like if you have 2 double bonds and they both make cis and trans isomers. You can remember, just giving you a recap of what cis and trans isomers were. That I told you that around the double bond, you have this shape. It's fan-shaped, right? So the thing is that when you have a molecule where you have a double bond and it's got 2 different groups attached and it's got 2 different groups attached over here. The thing is that the molecule could have 2 different 3-dimensional shapes. That it could either be, it's like connecting 2 fans. It could be that the H atom might be bonded to this carbon atom and it's pointing upwards. And on the next carbon atom, the H atom might be bonding or pointing downwards, right? Or there could be another version where the H atom is still connected to the same carbon atom, except that this time it's pointing upwards. And the Cl was pointing upwards. Over here, the Cl is pointing downwards. So there would be two different 3-dimensional shapes of the molecule, which are known as stereoisomers. So this would be, I mean, this particular one would be, you're going to call this 2 to the power 1. I mean, you're going to get 2 isomers, like you just have 1 double bond. Hani, is this clear for 1 double bond? Is this clear?
Yes, sir.
So I told you, if a molecule has 2 double bonds and this double bond is also making cis and trans isomers, this one is also making cis and trans isomers. This double bond, the carbon atom, I mean, the condition is you need to have a double bond and the carbon atom must be bonded to 2 different groups. And this carbon atom must be bonded to 2 different things. So the 3-dimensional shape of the molecule would be that this double bond could either be in cis form or it could be in trans form. And this double bond as well could either be in cis or trans form. So I've drawn all the combinations. They kind of look the same and they are, I mean, connection wise, they're identical. Like this carbon atom, every time fluorine is bonded to this carbon atoms, but sometimes it's pointing downwards, sometimes it's pointing upwards, sometimes it's pointing downwards, right? So the overall 3-dimensional shapes of the molecule, there would be 4 different shapes. I mean, this would be 1 double bond, 2 double bonds. So 2 to the power 2 would be 4. So Hani, is this clear?
Yes, sir.
So the same goes for this molecule. That if you have 3 double bonds, then the type of molecules that you're going to have 8 different stereoisomers. I mean, this particular thing can have 8 different 3-dimensional shapes. Okay, so I'm going to draw one of them. The first one is trans, the middle one is cis, and the last one is trans. So the middle one is cis. That means cis means that the H atoms must be if you focus on this double bond, cis means that the H atoms must be pointing in the same direction. So I've pointed them downwards. The first one was trans. So I ensured that this double bond, the H atoms, one is attached to this carbon atom, the other one is attached to this carbon atom. So in trans, the H atoms are pointing in opposite directions. And the last one is also trans. So I'm going to continue on from here. So this carbon atom would be connected to the last double bond. and that double bond would also be fan shaped. And let me just quickly correct this. So the last double bond would also be fan shaped. And I want to make it trans. So to make it trans, you got an H atom on one carbon atom, H atom on the other carbon atom. So they must be on different carbon atoms, but pointing in opposite directions. And the Cl must be pointing, I mean, that's the only place left. So that's our trans molecule. Okay, so that's one version of the molecule. So there would be 8 different versions of this molecule. So is this clear to everyone, this thing?
Yes, sir.
Because Zahi, is this clear? Mariam, Hani, is this clear?
Yes.
Yes, sir.
So just remember that 2 to the power n. But remember, this was for unsymmetric alkenes. Unsymmetric alkenes were where the molecule had no symmetry, where the right side and the left side were different. I mean, you've got an F, you've got a Cl, so it is clearly different. This one was also an unsymmetric alkene. I mean, the one over here. That you got a Cl over here, you got an F over here. So both sides were kind of different. As anyway, so just hold on one second. Acha. So let's talk about Acha, things would get slightly trickier over here. TK, it's going to be, we're going to talk about because you can be asked questions about symmetric alkenes. Now, what's going to happen if your molecule was symmetric? So we're going to talk about that. So symmetric alkenes. Just hold on one second. Let me reload this board. 1 second. Let's just wait 1 minute for the azan. Let me copy this. So what I've done is I've just removed the F in the example that we did, and I've replaced it with Cl. That kind of makes the molecule symmetric now. Like if you look at this molecule, it's symmetric now because the right side is exactly the same as the left side. I mean, it's got symmetry. Like if you look at the left and right side of this molecule, they're both identical. So that's what a symmetric molecule is. So this molecule now has symmetry. And the same I've done over here. I've just replaced the F. This one could exist in cis and trans versions. This one could also exist in cis and trans versions. Now, the thing with, is this clear? What a symmetric molecule is? Is this clear to everyone?
Yes, sir.
Yes, sir.
Okay. So now the thing is, the molecule looks exactly the same. You go from left to right, or you go the other way around. Okay, right to left. So it kind of looks exactly the same. So the thing over here is now that that this is a symmetric molecule, and left to right, right to left is exactly the same. So that means initially you have 4 versions. The first one is that both of them are in the cis form. I mean, that's the first one. The second one is, the first one is the cis, and the second one is in trans form. And then you have this one. You've got a trans. The first one is in trans form, and the second one is in your cis form. And then you have the last one, which is both of them are going to be in trans form. Okay, so both of them are in trans form. Now, this particular molecule, the problem with symmetric is left to right, right to left is exactly the same. So that kind of makes the middle one, the ones that I'm highlighting over here, these ones. The cis and the trans version, and the trans and the cis version, they are kind of exactly the same. Because going left to right, like if the first one is cis and the second one is trans, or going right to left, the first one is cis and the second one is trans, they would be exactly the same. And I can show you that they're exactly the same because we have drawn them. So just remember that they would be exactly the same. So we've drawn them. We've drawn the cis and the trans. I mean, this one. And we've drawn the first one as trans and the second one is cis. So both of them are with us. So what I can do is I can show you that they're both exactly the same. Although they look kind of different, like the CL is pointing downwards, the CL is pointing upwards. I mean, they look different, but if you observe carefully, then you'll notice that they are exactly the same. I mean, these two. The cis trans is the same as trans cis. I say at the moment it's not. I mean, the CL is pointing upwards. Over here, the CL is pointing downwards. Over here, the CL is pointing upwards. Over here, the CL is pointing downwards. Basically, they're flipped around versions of each other. So if I just rotate one of them and you then have a look, then you would notice that every atom is pointing in exactly the same direction. You got the 2H atoms pointing upwards. You got the 2H atoms pointing upwards. You got the Cl over here that's pointing downwards. You got the Cl over here that's pointing downwards. You got an H that's pointing in this direction. You got an H that's pointing here. You got an H that's pointing upwards. And you got a Cl pointing downwards. You got an H and a Cl pointing downwards. So they are exactly the same because of symmetry. So they are at this point exactly the same. So is this clear? This thing?
Yes, sir.
Yes, sir.
Okay. So questions have been asked about this. Okay. So be careful. So so the thing that you should remember, I mean, you don't, if you just want the shortcut, that is that normally if it's 2 to the power n, I'm just going to write the summary over here. Normally if it's 2 to the power n, right? I mean, remember what 2 to the power n is. That you got 2 double bonds. That means you're going to get 4 isomers. If you have 3 double bonds, you're going to get 8 isomers. Similarly, if you've got 4 double bonds that are making cis trans in a molecule, then that would be 16 isomers. But then the symmetry thing, that is only true if it's not symmetric. If it's symmetric, so I'll just summarize everything. ठीक है, in this here, that is, if you've got unsymmetric, so you got unsymmetric double bond and it's making cis trans. Then it's 2 to the power n if it's unsymmetric. Okay, so you should know that there would be, depending on how many double bonds are making cis trans. Vice versa, if it's symmetric, that means left to right, right to left, it's the same thing. And the double bonds are making cis trans. So if it's just one, you basically get one isomer. If it's 2, you should get 4 isomers. I mean, it's going to be, for 1, it's going to be 2 to the power 1. That would be 2 isomers. I say if it's 2 to the power 2, you should get 4 isomers. I mean, previously you would get 4 isomers, but now you're going to get just 3 isomers. I mean, you can just remember that. You're going to get 3 isomers, just the way, because if it's symmetric, then out of the 4, 2 of them are going to be exactly the same. So you're going to count them as 1. I mean, this is just 1. They're exactly the same. So it's 1, 2, and these 2 would be the same. So that would just be 3. And the same goes if there are 3 double bonds, you should get 8 isomers. But due to the symmetry, some of them would be exactly the same. So instead, you're going to get 6 isomers, not 8. Okay, so this thing, you can just remember. Now remember, and I'm going to sum it up. Okay, most questions are about just one cis trans. 90% of the questions would be, there's just going to be one double bond and it would be making cis and trans isomers. So most of the questions would be just about this. That's it. You got a double bond. Is it making cis trans or is it not making cis trans? That's it. Very few questions would be on multiple double bonds that are making cis trans isomers. So this would be very few questions on this. And even fewer, basically just probably 2 questions in 10 years would be on this thing. What if you have multiple double bonds and it's symmetric as well? So then some of the isomers would be identical. Some of the combinations would be identical because of the left and right to left. Like you flip them around, they kind of look exactly the same. So you don't have to worry that much about this. Most of the questions would be on one double bond making cis trans, very few on these ones. Achha, but is this clear? Yes or no? Is this clear?
Yes.
Okay, Abdullah, is this clear? Alicia, is this clear?
Yeah.
Achha, so we can now, what we can do is we can try and we're done with isomers. Okay, one last thing about isomers is that all isomers have kind of different properties. The reason they have different properties is because they all, even if it's a stereoisomer, they would behave differently. Because remember, biological molecules are very shape specific. I mean, for example, molecules, they have a lock and key system. Like a particular shape of a molecule would fit with another molecule because if the shapes match and the groups match, then they react. That's how biology works. The red blood cell has a very specific shape. If the shape gets disturbed, it's not able to capture the oxygen. So everything is shape specific. So if the CL was supposed to be pointing upwards and the CL is pointing downwards, then some of the reactions might not happen. So pretty much everything is affected. So isomers always have different properties, chemical properties, different functionality. And I told you about stereoisomers specifically, that they are very hard to make. For example, this one is the right shape. This one might not. I mean, when you're making medicines or when you're making any or like in agriculture, like chemistry is everywhere. So you're trying to make this molecule, but there are different three-dimensional versions of this molecule. So it's pretty hard to get the right version. That's why medicine has so many, allopathic medicines have so many side effects. Because when you know that this molecule would work, but there's going to be one very specific shape that's going to work. Not all four of them. Over here. So you want to make this molecule, you can make this molecule. Making this molecule is not the tough part. The tough part is making the right shape of the molecule. There are 4 different shapes of the molecule. So making the right shape of the molecule, that's the tough part. So which is why medicine and pretty much everything that's related to chemistry, specifically medicine, has so many side effects because of this. You take a vaccine, why do you have side effects? Because the vaccine will have different versions of it. There's only a couple of versions that would work. The other ones might cause something else. The groups might be pointing in different directions, which is why you're going to have side effects. You're going to have fever. You're going to have reactions with it. So that's the reason why medicine a lot of times causes more harm than the good effect. Medicine usually, most medicines, especially it's better to avoid medicines as much as you can, unless you get very sick, then you are dependent on medicines. But most medicines, we have not been able to actually figure this out properly now. And the same goes for chirality. We talked about chirality. One of the molecules is going to work perfectly. The other one is not going to work because the bonds are pointing in different directions. They're mirrored versions of each other. It's just like your glove and your hand. If you've got a right glove, your right hand would fit into it, not your left hand. Even though your right and left, they kind of look the same, but they're not exactly the same. You can try fitting your left hand into a glove that says right hand. It's not going to fit. Your thumb would be pointing in the opposite direction, so it's not going to fit. So the thing is, biology works like that. The molecules kind of fit together, they lock with each other. There's a lock and key system, and unless they can't properly fit and they can't properly match, they're not going to react. So let's sum this up. The last thing was that even though they're stereoisomers, they're going to have different properties, different chemical, different physical properties, and there's going to be variation in those. So let's start. All isomers would have some differences. So let's start with past paper questions, and we can start doing the first one. Okay, now this would have pretty much all types of isomerism. So the first one is, what is the total number of different chloroethanes where n can be any integer from 1 to 6? So we can try and do that. So you're saying you have to interpret or comprehend the question properly. It's C2. H is 6 minus n, and you've got Cl, which is n. Now, he's saying n could be any number from 1 to 6. So if I start writing this, n could be 1. So that's C2H5 and 1 Cl. N could be 2, that would be C2H4 and 2 Cls. N could be 3, so it's going to be C2H3 and 3 Cls. N could be 4, so it could be C2H2 and Cl4. N could be 5, it's going to be C2H1 and Cl, 5 Cls. And then n could be 6. So C2, H would become 0 and Cl would become 6. So you're going to get these many different molecules where n can be any integer from 1 to 6. But the thing is that each one would form isomers. So the question is not over yet. It's you have to look at each one of them. Is this clear so far? You're going to get 6 different molecular formulas. But each one is going to have further isomers, like the first one. The first one, it's got 5 hydrogens and 1 Cl. So that's only one version, TK. So no issues there. The second one, it's got 4 hydrogens. So here are my 4 hydrogens, and it's got 2 Cls. But the thing is, this one will have 2 versions. One of them would be that the Cls might be on opposite carbon atoms. right? So this particular molecule with 2 Cls, the 2 Cls could be on the same carbon atom or they could be on opposite carbon atom. So there would be 2 versions of this one. Is this clear?
Yes.
Yes.
So then the third one, it's got 2 carbons and 3 Cls now. So you could have 3 Cls on one carbon atom, right? And you could have the 8 atoms on the other one. Or you could have another version which could be 2 Cls on one carbon atom and 1 Cl on the other carbon atom. So that's another version. And I don't think there's any other combination. 2 Cls on one, 1 Cl on the other one. That's it. 4 Cls. How many different versions would you have for 4 Cls? So you could have 3 Cls on one. The 4th Cl could go on the other one and you got 2 H's. Or there might be another one, which would be that you could have 2 Cls on one carbon atom and 2 Cls on the other carbon atom. And the 2 hydrogens are over here. So then this one would be 1, like 5 Cls. You don't have a choice. 3 Cls on one and 2 Cls on the other one. That's H. And then you have this one. 6 Cls. So that's all of them would be Cls. So that's only one. There's only one combination for this one. So all of them would be Cl. So it looked like an easy question, but it's not. It's you had to waste a lot of time drawing all of them. So in total, how many do you have? 1, 2, 3, 4, 5, 6, 7, 8, and 9. So 9 is the answer. So he was asking how many different chloroethanes where N could be 1 to 6. So I wrote down all the formulas. And then each one had different isomers. The first one had just one. The second one had 2 of them. 2 Cls on the same carbon atom, 2 Cls on opposite carbon atoms. The third one had 2 versions as well. It had 3 Cls, so 2 Cls on one, 1 Cl on the other one, or 3 Cls on the same carbon atom. 4 Cls also had 2 versions, 3 Cls on one, 1 Cl on the other one, or 2 Cls on one, 2 Cls on the other one. So is this question clear, this one?
Yes.
Yeah.
So let's do more isomer questions. Remember, isomer questions are kind of, most of the time, they're kind of difficult. But the thing is that, especially in theory, a lot of questions, they actually begin with isomers. So you have to be very good with isomers. This is just a question on structural isomers, TK. So we'll practice more questions next class then, TK. Okay, everyone.
Allah Hafiz.
Allah Hafiz.
Allah Hafiz.